Okay, hello everyone and welcome to the second part of a warm summary on reinsurance. In this part, we're gonna talk about the, the part where we're working with a particular distribution. So let's have a quick recap that why we're going to have this chapter, what this chapter is, what this part is gonna be about. Okay, so from the last part, in excess of loss, the insurance, if we have a look into the formula here, we will see that we have to work with integral of x fx a couple of times, like when we have to find the expectation of the amount of claim paid by the direct insurer or the reinsurer, right? Sometimes we need second moment, the integral of x square fx, but it's not actually the second moment because it's not to infinity, it's capped at the retention limit. So in this part, we're going to talk when this fx is particular distribution where the integral can have a nice formula for us to working with, which are the log normal distribution and the normal distribution. So let's see. First, let's have a look at the log normal distribution. The log normal distribution, when we have the integral of x to the power of k, x from L to U, we can have a very nice result as we see. Okay. Here you can see UK and LK. This is the kind of function that we have from the U substitution during the integral process. And here is what they mean. This capital phi means the area under the normal curve that behind the value in it. So let me have a note here a little bit. This phi is mean phi of x is just probability that the standard normal will take a value less than x. Alright, this is how it works. Okay, so let's have a look into a proof a little bit. The proof can be done by just take a u substitution of t equal to log x, take away mu divided by sigma, and then take away k of sigma. This one is part that I will leave you to read, so I just skip to going through it, but you can have a read anyway. I already paste it for you. And let's take a note about the lower and upper limit a little bit. So when L equal to 0, let's see the function of Lk. The function of Lk will take log of L, take away mu, so log of L will take the value that tend to negative infinity. So when phi of negative infinity, when we calculate it, is 0, right? Because it's not is none of the area under the normal curve. And then the phi of 0 is a half, right? Because we have a symmetric property of the normal distribution. And lastly, the phi of infinity, which is the whole area under the normal curve, will give the value of 1. Okay, so let's see how to use them by the example. Okay, so here we have fx. We have a PDF of a log normal with a mu equal to 7.5, sigma square equal to 0.85 square. Let the part A asks us to find the integral from 1000 to 5000 fx. So this one is the case where x equal to 0. So when x equal to 0, we have this part going to 1 because we have e to the power of 0. So what we're gonna have here is just phi of log 5000, take away mu divided by sigma, and then take away capital phi of log 1000 take away 7.5, and then divided by 0.85, the sigma. Okay, so you just plug in the number in parentheses in your calculator. You will have the phi of 1.196698, and then take away phi of negative 0.696759, which is 0.884288. Take away 0.242977. This part you just have a look into a table, or if you have any kind of applet, you may try to use it. Okay, so the answer we have here is 0.641311. Here we are. Okay, and then part B. Now we have the integral from 0 to 1000 of x fx dx. So now the k is not 0 anymore, the k is 1, so we have e to the power of k mu, which is mu because k equal to 1, plus 1 over 2 sigma square 0.85 square. Okay, and then we have the phi of the upper bound, which is log 1000, take away 7.5 divided by 0.85, and then take away one more sigma, right? Because this is k equal to 1. And as I tell you earlier, the L, the lower bound of 0 will give the phi, capital phi of negative infinity, which is 0, so it minus 0. So we can just ignore it, right? Then we put this number into our calculator. We have e to the power of 7.86125 multiplied by phi of negative 1.54 6759, okay, which is e to the power of 7.86125 multiplied by 0.060961, and then it will be equal to 158.179274. And here we are. Okay, let's work on the last one. The last one is now the case where k equal to 2. The last one, we have integral from 5000 to infinity of x squared fx dx. So when k equal to 2, we have 2 times mu plus 1 over 2 times 2 square, which is 2 of the sigma square, right? And then because the upper limit is upper bound, upper integral is infinity, we have 1 here. The phi of infinity is 1, and phi of log 5000, take away 7.5 divided by sigma, and then take away 2 more sigma. Right? Okay, plug this into a calculator. We have e to the power of 16.445 multiply 1, take away phi of negative 0.5 or 332 T02 here. Okay, so this one we comment on this one a little bit. Let's say if you have a table, you can plug in this number table to find the fee, the capital fee of this number. But let's say if you have some kind of applet, this is the normal curve, right? The standard normal curve. The number you are looking is here around negative of 0.5. So if you have a look into a table, the table you give an area here, and what we want is 1 take away this number, which is the probability on the other side. So if you have an app or something, you can ask for the probability that the x from standard normal we take a value greater than negative 0.5, this number. Okay, continue. This one we're going to have e to the power 16.445 multiply 0.692624, which is around 9 million, about 9 million and half a million. Here what we got, okay, and then we're done. Okay, now we move on to the next one, the normal distribution. When we work with normal, it's a little bit more complicated, right? Because we don't have a general formula for every x to the power of k like before. This one is just for one x, right? Just x, fx. And we have u palm, l palm here. This one is just the number take away mu divided by sigma. We don't take away more sigma like before. It's just this one, okay. And something that you need to be careful here is there is two type of phi function here, which is the lowercase phi function and the uppercase phi function. The lowercase is you plug this number into the probability density function of the normal distribution. So it's PDF, but this one is the DF. It's the area under the curve. It's not the same thing, okay? And here's proof. I paste it here in case that you want to read that why how we have this formula, where does it come from? But I will not gonna talk about it, so you can have read, okay? But anyway, we work on something similar as this proof anyway. So let's see. This one they ask us to find the formula for the expression of x squared fx, okay? So let's see what do we have. So first of all, the thing that they ask us to do is integral from L to U of x squared, and fx is 1 over square root 2 pi sigma e to the power of negative 1 over 2 x take away mu over sigma square, okay, dx. Okay, and now we just do something similar to what we have done before, which is we take the u substitution. We make z equal to x take away mu over sigma, right? So x will equal to mu plus sigma z and dx will equal to sigma dz. Okay, and then this one will be integral from u prime to L, from L prime to U prime, and U prime and L prime are the same expression as here. Okay, and what we have here is x is mu plus sigma z square 1 over 2 pi, square root 2 pi multiply sigma will cancel with this sigma we will have here, so we have just 1 over 2 pi square root 2 pi. We have this one, and e to the power of 1 over 2 that square. We have just this one, right? This at. Okay, so what we will have is, what we are going to do is we will expand this first part into 3 terms, right? And we'll do the integral separately. Okay, so the first one is the integral L prime to U prime, okay, of mu square, which mu square is constant. So we can pull mu square out, and we have inside 1 over square root 2 pi e to the power of negative 1 over 2 z square dz. This is standard normal distribution. So basically what we have here is just the mu square of phi mu prime, upper u prime, take away the capital phi of L prime. Okay, so we good. Let's move to the second term. The second term is plus 2 mu sigma z, right? And with all of that, just z that is not a constant, so just z will be set in the integral. After that, we can pull up. So we will have integral from the L prime to U prime of z 1 over 2 square root 2 pi e to the power 1 over 2 z square dz. Here what we will got, okay? And what we are doing is we just do a U substitution, right? So this one is equal to a negative of 2 mu sigma, and integral from z equal to L prime, z equal to U prime. We have it because we have to do one more time of a substitution, right? We have 1 over square root 2 pi and e to the power of u du. So in case of that you are confused, for u is just the negative of 1 over 2 z square. Okay, so we have du equal to negative z dz. Okay, so that's why we have a negative here, and this one come to u, this one just go away. Okay, so what happened when we integrate this one? What happened when we integrate this one is we just have e to the power of u again, right? Because we integrate e to the power of u du, and then we just put back our z, which means we're gonna have the negative of 2 mu sigma 1 over square root 2 pi e to the power of 1 over 2 z square. So we do integral here, and then we substitute by our bound. Okay, so finally we're going to have the negative 2 mu sigma of this one is just the PDF, right? The PDF of the standard normal. So it's our lowercase phi of u prime, take away the lowercase phi of L prime. Here we got, okay. And then the last part is the sigma square and z square. So we pull sigma square out, and we have inside the integral from L prime to U prime of z square, and other thing remain the same. So we have this, okay. So how we deal with this one? The way we deal with this one is we're going to do the integral by part, okay? We're going to do the integral by part because this one is the sigma square of the integral from L prime to U prime of z multiply z. I should put the parentheses here so it be more clear. Multiply 1 over square root 2 pi e to the power of 1 over 2 z square dz. Okay, this is what we have. And then when we do by part, we're gonna have the sigma square of z times the integral of this one. The integral of this one is the one that we was calculated before, right? This one, the integral is here, right? So we have the negative 1 over square root 2 pi e to the power of negative 1/2 of 1 over 2 of z square from L prime to U prime, right? And then the other part is just the integral from L prime to U prime of negative 1 over 2 1 over square root 2 pi. Just this part, because this part gonna be integrated, okay? So just negative 1 over square root 2 pi e to the power of 1 over 2 z square dz. Here what we have, and this one is just the sigma square. The first part is U prime, right? U prime, then this one is just the lowercase phi of U prime, but we have negative here, so we have L prime phi, the lowercase phi of L prime, take away U prime and lowercase phi of U prime. Okay, we have this one. we have this one for the first part, and for the second part, this is just the area under the curve, right? So it's capital phi from U prime to L prime. We have negative and negative, so it will solve in positive. And here's what we got. So the final task is to put the three terms together, which is, in case that you lost the track, is here the first term, the second term, and the third term. So this is the answer. We can do a little bit of grouping. So the final result is mu square plus sigma square of the capital phi function of U prime, take away the capital phi function of L prime. Okay, and then minus sigma of 2 mu per sigma U prime lowercase phi function of U prime, right? And then take away minus 2 mu per sigma L prime lowercase phi function of L prime. Here's what we have finally. Okay, and as I have done some question in this chapter, this thing is rarely asked. Okay, so you may don't focus on this normal distribution too much, but for the log normal, there is a lot of question in this chapter on this part that ask to work with the log normal distribution, so you better be familiar with this formula. And that's all for the second part of form summary on reinsurance. Thank you.